What happens when the system everyone relies on simply cannot go down? Ever. In this module, you'll see how to design blockchain-based trust layers that stay online through failures, attacks, and disasters, so mission-critical services remain verifiable and uninterrupted. In enterprises and governments, blockchain-based trust isn't a nice-to-have experiment. It underpins systems where downtime or data corruption becomes a business crisis or even a legal incident. Think of high-value payments, cross-border supply chains, or public registries. In all of them, consensus safety and data integrity can't be best effort. They must survive hardware failures, operator mistakes, cyber attacks, and even partial network collapse. High availability, resilience, and disaster recovery solve different parts of the same problem, keeping a trusted service usable under stress. High availability is about minimizing downtime in normal failure conditions, often expressed as a 99.99% uptime target. Resilience is the system's ability to absorb shocks, degrade gracefully, and avoid catastrophic cascades. Disaster recovery assumes something really bad happened and focuses on restoring both the service and its state. For blockchain-based trust, there's a crucial nuance. Every continuity plan must preserve consensus safety and auditability. After an outage, nodes may come and go, but the ledger's integrity and history must remain unambiguous. When we say indestructible node, we're really talking about engineering a node so failure becomes just an event, not an outage. At the compute layer, clustering keeps service alive. If one instance dies, another is already running or ready to take over. We also separate concerns. Edge and API components are isolated from the consensus core, so you can scale and expose services without risking the trust anchor. Storage is built on the assumption of failure too. RAID, cross-zone disks, and replicated volumes protect ledger state. And underneath it all, everything is defined as code, so you can recreate a compromised or failed node quickly, predictably, and compliantly. Consensus liveness asks a simple question. Can the network still make progress when things break? Topology is the first lever. A richly connected mesh-style network with multi-homed links gives validators multiple independent paths, so a single router, data center, or ISP failure doesn't stall block production. BFT consensus also assumes some number of faulty or malicious nodes. As long as the number of bad or unreachable nodes stays within that bound, the protocol keeps committing blocks. Location diversity then closes the loop. Placing nodes in different regions and on different providers prevents one outage from silently taking your entire trust layer down. Consensus liveness isn't enough on its own. In enterprise and government settings, you also care about who is in the quorum and where they sit. Quorum diversity means validators are deliberately spread across multiple regions, multiple clouds, and at least one on-premise environment. That way, a regional outage, a single cloud provider failure, or a data center incident can't halt the ledger. You also build in jurisdictional diversity. If one country issues a freeze order, the network can still reach quorum in other legal zones. Designing quorum diversity upfront turns your blockchain from highly available servers into genuinely resilient trust infrastructure. Immutable backups are your last line of defense when everything else goes wrong. For a blockchain-based trust platform, it's not enough to back up only the ledger files. You need consistent copies of the block store, the state database, and the cryptographic keys, all tied together so they can be restored to a coherent point in time. Continuous log shipping gives you near real-time recovery points, but immutability comes from writing those backups into offsite, offline, worm-style storage. That combination breaks the attacker's control plane. Even if validators, admin accounts, or primary storage are compromised, you still have a clean, legally defensible history that ransomware and rogue insiders cannot rewrite. Reconstructing state really answers one question. If everything broke, could we mathematically prove what the system should look like now? The backbone is protocol finality. Once blocks are finalized, they become an anchor of truth. On top of that, you take periodic snapshots, validated captures of the full state at specific heights. If a node fails, it doesn't need to replay from Genesis. It restores the latest trusted snapshot, then replays only the newer finalized blocks. This combination of anchored snapshots plus replay is what makes recovery both efficient and auditable in regulated environments. Merkle trees and hash chains give us mathematically strong evidence about system state. Each transaction is hashed, then combined up the tree to a single Merkle root. If even one bit of a transaction changes, the root hash changes, and that mismatch is instantly detectable. Consistency checks compare what a node stores against these routes in block headers. Cross-validation then lets independently restored nodes prove they reached the same state without trusting each other's copies. Over time, the chained hashes across blocks form an audit trail that's extremely hard to forge, supporting legal evidence, investigations, and regulatory assurance. Your blockchain network should be treated as just another critical system inside your enterprise business continuity plan, not something special on the side. Start by tying it firmly into identity. Who can operate nodes, manage keys, and approve failover actions? Those roles must exist in your IAM and DR documentation. Then map all dependencies: DNS, HSMs, key vaults, message buses, monitoring. If any of those fail, consensus or client access may break. Integrate with security operations so SEM alerting and incident response processes explicitly cover the ledger. And finally, rehearse cross-team drills, including legal and compliance, to validate recovery and governance in realistic scenarios. In mission-critical blockchain deployments, success during an outage is defined by two numbers: RTO and RPO. RTO is about time. How long you can afford to be down before service must be restored. A payment rail for salaries may tolerate hours. A border control system may tolerate seconds. RPO is about data, how much committed work you can afford to lose. In many government and financial contexts, the target is effectively zero. With blockchains, there's a hard constraint. RPO must respect consensus finality. Once blocks are finalized, you can't roll them back just to meet an aggressive recovery objective. Your DR design has to work with that, not around it. In a regulated blockchain environment, failover cannot be improvised. You begin by defining precise triggers. What exactly constitutes an outage, corruption, or security event that forces you to move? Once a trigger is hit, automation should take over. Promote standby validator nodes, reconfigure clients, and update integration endpoints without human guesswork. Next, you stabilize trust anchors. Rotate or reissue keys, update DNS and endpoints, and ensure auditors can trace every step. The last phase is returning to steady state by resynchronizing ledgers, rejoining nodes, and formally closing the incident. Every one of these actions should be encoded as infrastructure as code and rehearsed, not invented during a crisis. Assurance is about proving your blockchain-based trust layer survives real-world chaos, not just passing design reviews. You deliberately try to break the system before attackers or outages do. That means injecting faults in production-like environments, simulating data center or region loss, and rehearsing how people and governance processes respond under pressure. The goal is continuous. Adversarial testing so resilience improves over time, and unknown unknowns are discovered on your terms, not in a public incident. Think of blockchain-based trust as a fortress you design, not a product you buy. At the core is the data itself, modeled for immutability, verifiability, and auditable recovery. Around that, you engineer resilient infrastructure with redundant nodes and hardened platforms. You then shape the network: mesh-style connectivity, secure channels, and controlled entry points between organizations. Over all of this, you enforce a protection layer of security controls, monitoring, and incident response. And it only works when governance ties everything together: clear ownership, playbooks, and continuity plans. In mature deployments, resilience isn't an add-on. Resilience is the architecture.